Bismillahirrahmanirrahim. Welcome to the course of Electric Machine 2, lecture number 12. Today we are going to study the equivalent circuit of a synchronous motor, pull-out torque, and synchronous motor V-curve. Up till now we have covered the synchronous motor in detail and its related topics. Today is our last lecture on synchronous motor. The equivalent circuit of a synchronous motor will revise and remind the things that how it works. So the synchronous motor is connected to two electrical system, that is a DC source at a rotor and an AC system to the stator terminal. When operating at a normal synchronous motor, no voltage is induced in the rotor by the stator field because the rotor winding is rotating at the same speed as the stator field. Mean at a synchronous speed, when the motor is rotating, there is no voltage induced in the rotor. Only the DC is present in the rotor winding, and ohmic resistance of this winding is the only opposition. There is the only DC supply to the rotor terminal, and there is a ohmic resistance because the winding is made up of copper. So in this condition we have only the ohmic resistance, and it is shown in the figure. This is the rotor circuit in which there is the current IF, this is the DC supply, and that is the winding of the rotor. Now let's study the stator circuit. In the stator winding, two effects are to be considered. The effect of stator field on the stator winding, mean the field that is produced by the stator, its effect on the stator winding, and the other one is the effect of the rotor field cutting the stator conductor at synchronous speed. So first of all, the effect of stator field on stator conductor is accounted for by including an inductive reactance in armature winding. This is called synchronous reactance XS. A resistance RA must be considered to be in series with this reactance to account for the copper losses in the stator or armature winding. So the first effect is the stator field on the stator conductor. So for this we include inductive reactance in armature winding, which is called a synchronous reactance XS, and a resistance RS in series with this reactance, that is for the copper losses. Both of them, XS and RA, combinedly called a synchronous impedance. So this is the synchronous combined with the synchronous reactance and give the synchronous impedance of the machine. The second effect is that a voltage is generated in the stator winding by the synchronously revolving field of the rotor, is shown in figure. This is the figure. This is the synchronous impedance XS and RA, and this is the induced voltage, which we call back EMF. So this is the equivalent stator current, the supply voltage, the impedance, and the back EMF, and this is the rotor. So both of them collectively we call the equivalent circuit, having stator circuit and rotor circuit. So the effect is that the voltage is generated in a stator winding by the synchronously revolving field of the rotor. The generated EMF EB is known as back EMF and opposes the stator voltage or the supply voltage. The magnitude of EB depends upon the rotor speed and the rotor flux per poles. Since rotor speed is constant, the value of EB depends upon the rotor flux per pole, that is, the excitation current IF. So this is the equivalent circuit of a synchronous motor. Next one is pull-out torque. Pull-out torque. There is a limit to the mechanical load that can be applied to synchronous motor. As the load increases, the torque will also increase. We already studied that by increasing the load, the speed or the synchronous remain. So there is a limit, and as the load increase, the torque will also increase. The stage reach when the rotor is pulled out of synchronism and the motor come to standstill. The low torque at which the motor pull out of synchronism is called pull out or breakdown torque. Its value varies from 1.5 to 3.5 times the full load torque. When a synchronous motor pull out of synchronism, there is a major disturbance on the line and the circuit breaker immediately tripped. This protects the motor because both squirrel gauge and stator winding heat up rapidly when the machine is out of the synchronism. So we need to trip the circuit breaker or off or automatically it off, because when this happens, the squirrel gauge and stator winding heat up quite rapidly. The next one is the synchronous motor V curve. This is the graph plotted between the armature current IA and field current IF. Its shape is similar to the letter V, thus we call it V curve of synchronous motor. We know that the power factor of synchronous motor can be controlled by varying the field current IF. As we know that armature current IA changes with the change in the field current IF. So this is the V curve. The minimum position on each curve denoted the unity power factors, and on the left hand side we have a lagging power factor, and on the right side we have leading power factor. Initially, suppose at no load, when we increase the DC field current, the AC armature current start to decrease until it reached to a minimum value, which we call a power factor, unity power factor. After this, when we increase the DC field current further, the armature current start to increase, and it is in the leading or it is overexcited in this position. So that's why it is in the leading position. Same for the half load and full load. This is in the form of V, so we call it V curve, and from here we can see that the unity power factor is at the minimum position. So this is all for the today lecture. Thank you.